Hi there. In this presentation, we'll talk about linear algebra and its applications on healthcare monitoring. Let's get started. There are many apps which depends on linear algebra, and you can see lots of them in your daily real life. But we will focus on healthcare track, especially on the concept of tomography. First trial was for Röntgen. When he tested it on his wife's hand and he saw its interior. And it was the first photograph which generated with radiograph. Let's get into the main purpose of this presentation, which is linear algebra rule. Suppose that this figure represents a medium in the shape of squares, which is composed of 3 by 3 grid of smaller squares. Each smaller square can either absorb one intensity unit from the X-ray beams. For example, the white squares or not absorb any intensity at all, for example the black squares. We can think of the white squares as bone and the black squares as air. To make the model more tangible, the data we receive from running a CT scan is the total loss of intensity units for each row, column, and diagonal that an X-ray beam passes through. That is, if an X-ray beam passes through the first row in the figure, the data tells us that two intensity units have been absorbed in the medium as we continue to radiate the medium. After knowing the concept, we can talk now about the machine that takes the image of the body. This machine basically depends on angle calculated, and these angles made up of a set of line integrals. In X-ray CT, the line integral represents the total attenuation of the beam of X-rays. It travels in straight line through the object, and we can collect this info to take an image of these attenuations by taking the different angle photos in one composed photograph. It's obvious now that attenuation when transmission is the problem which we have to encounter, and we can solve this problem by these steps of radon transform and the other problem that taking the inverse of the transform, then we will use Fourier transform. Theoretically, the data are line integrals of the function of interest, but in practice, we never have the line integrals totally. Ultimately, we will construct a discrete image made up of finitely many pixels. Consequently, it can be assumed without loss in generality that the attenuation function to be estimated is well approximated by a function that is constant across small squares called pixels, and that the goal is determine these finitely many pixel values. And for more illustration for forming a JPEG image, we can look at this figure and video for a few moments, and next we will discuss derivation of the system of equations we need to form this image. We shall see how the construction of a cross-sectional view of a human body by analyzing X-ray scans leads to an inconsistent linear system of equations. The field of view is divided into 1 to n pixels. Our aim is to get equations of these pixels or construct a system or as we saw previously in the last slide. Let's go. As shown, we first will calculate xi, which equals to ln in the denominator number of photons entering the jth pixel divided by the denominator number of photons leaving the jth pixel, which equals to ln fraction photons passing the jth pixel without being absorbed, where ln denotes the natural logarithmic function as known. If the X-rays beam passes through an entire row of pixels, then the number of photons leaving one pixel is equal to the number of photons entering the next pixel in the row, If the pixels are numbered 1, 2, 3 to n number, then the additive property of the logarithmic function gives x1 plus x2 plus etc xn then will equal to len number of photons entering the first pixel divided by number of photons leaving the last pixel. After that, by the beam density of the ith beam of a scan denoted by bi, we will calculate bi as equal to len of number of photons of the ith beam entering the detector without the cross section in the field of view divided by number of photons of the ith beam entering the detector with the cross section in the field of view equals minus len fraction of photons the ith beam passes through the cross section without being absorbed. The denominator in the first expression for is obtained by performing a calibration scan without the cross section in the field. The resulting detector measurements are stored within the computer's memory. Then a clinical scan is performed with the cross section in the field of view at the of all beams constituting of a scan are computing. The values are stored for further processing for each beam that passes squarely through a row of pixels. To this point, we are calculating two parameters xi for each pixel of the image and bi for each pixel either. If we calculate each of them, a fraction of photons of the beam that passes through the row of pixels without being absorbed equals to fraction of photons of the beam that passes through the section without being absorbed. Thus, if the beam passes squarely through a row of pixels, then x1 plus x2 etc equals bi. This equation is known from the clinical calibration measurement nd to our unknown pixel densities that must be determined. If we generalize this equation, if we set aij equals to 1, if j equals j1, j2, j2 to ji, or 0 or otherwise, then we may write this equation as ai1 x1 plus ai2 x2 etc. equals bi. As we see, beams of a scan is not necessarily pass through a row or column of pixels, but instead a typical beam passes diagonally through each pixel in its path. There are many ways to take this into account. In this figure, there are three methods of defining the quantities that appears in equation 3. And the results will be resulted as shown in the three equations below, and you can check it. So now in this way we have a linear system of m equations is in n unknowns. The n is pixel densities. Depending on this number of beams and pixels used, we may have m greater than n or m equal to m equal to n, or m is less than n. Only the case when m greater than n is considered, which gives rise to an overdetermined system of equation in which there are more beams in the scan than pixels in the field of view. Because of inherent modeling and experimental error in this problem, we cannot expect the above linear system to have an exact mathematical solution for this pixel densities. The above overdetermined system can be solved using the well-known method of least squares method. We will stop here for minimization of duration of this video. For more understanding and information about this topic, you can check the links below. Thank you for watching.